Assalamualaikum and good afternoon to everyone. We are from DSP HomeGroup3 and we are going to present on filtering noise in audio signal using DSP. So for the introduction problem statement, in this phase we are required to create a filter to remove the background noise that has corrupted the audio signal from the file ecg2.3.met. So the task is given as the following.
So the ECG signal was plotted in both time and frequency domain. We used 200 Hz sampling frequency with a period of 5 milliseconds for 10 seconds using this and also this function for the time domain signal. So below is the time domain input ECG2 in continuous signals and also time domain input ECG2 in discrete signals. Next, we plot the ECG2 signal in frequency domain. So for frequency response, we use this function to perform Fourier transform response. So below is the ECG2 signal in frequency domain. This one is the noise at the negative regions and also this one is the noise at the positive regions. So below is the ECG2 signal in the frequency domain for the positive region. And we can clearly see that there is a noise at the 50 Hz frequency.
Moving on to filter design. Firstly, we have the IIR notch filter, which is a bandstop filter. To remove a 50 Hz noise from a signal sample at 200 Hz, we set the center frequency as 50 Hz. We set the Q factor of the filter to 45 and use it to specify the bandwidth. We can get the numerator and denominator coefficients of the IIR notch filter from the function, and from the coefficients, we can get the transfer function. To plot the frequency response of this filter, we can use the freq_z function. We can see from the frequency response that there is a very sharp attenuation at 0.5 normalized frequency, which is where the noise is located at. To plot the poles and zeros of the filter in z-plane, we can use the z-plane function. Next, we have the IIR low-pass Butterworth filter. The filter order is set to 5th order. The cutoff frequency of the filter is set at 40 Hz. The sampling frequency is 200 Hz. After getting the filter coefficients from the Butter function, we can get the transfer function as shown. We can get the frequency response of the filter by using the function above, and this is the magnitude and phase response of this filter. And this is the plot of the poles and zeros of the filter in z-plane.
The third filter design is the FIR low pass filter Hamming. The filter order is set to 8th order. The cutoff frequency is set to 40 Hz and the sampling rate is set to 100 Hz. By inserting schooling, we will get the equation. So to get the frequency response magnitude and phase, we insert the coding freq_z. And finally, to get the poles and zeros, we use the function z-plane.
First, let's look at the time domain for the IIR notch filter output. And we see that the blue color is the output and the red color is the input. So you can see that the output and the input are in phase. Next is the time domain of the IIR Butterworth low pass filter. And for this result, you can see there's a phase delay between the output and the input, as same with the FIR having low pass filter. And the reason why IIR notch filter don't have the phase delay because its phase response is constant. And next is the frequency domain for the output. And the first one is using the IIR notch filter. The second one is IIR Butterworth low pass filter. And the 50 Hz spike are gone, you can see that. But for the FIR low pass filter, even though the magnitude of the spike was attenuated, but still and there and require more order to totally filter out. So next is the phase response for IIR notch filter. And you can see that the phase response was not changed except on the cutoff frequency region. But for the IIR Butterworth low pass filter, the phase response on the pass band region was changed significantly. Last was the FIR low pass filter, and the phase response on the pass band region was not changed. So the last is the output of the ECG signal. You can see that there's a noise on the come from the IIR notch filter and also FIR having low pass filter, and you still got the fluctuating signal on the output, right? And but for the ECG signal for the IIR Butterworth low pass filter, the result is perfect. So this is a summary of the filter, and the conclusion is that the IIR Butterworth low pass filter we're choosing in this assignment because IIR Butterworth low pass filter can totally filter out the noise for the ECG signal. Although IIR Butterworth low pass filter have phase different, but since our ECG is a periodic signal, right? So it doesn't affect the overall output. But even though FIR have a more linear phase response, but it require more order to filter out the noise. But for the Butterworth filter, only need 5 order can filter out the noise, and it have more linear phase response compared to other type of IIR filter. So that's all for our group 3. Thank you for watching.